In a previous video, we talked about how atoms bond together. Now we are going to talk about how they arrange themselves. Do they pack together with no rhyme or reason? Or is there some pattern to the way they organize themselves? Well, kind of both. It depends on the material and sometimes how it's processed. The atoms in some materials take an ordered pattern, very regular. We call this type of material crystalline. Gold and normal metals and many ceramics are crystalline materials. If the atoms arrange themselves in no discernible repeating pattern, we call this type of material amorphous. Normal polymers and glass are amorphous. With crystalline materials, it becomes more fascinating when you look even closer. These regular patterns take on particular shapes that are like building blocks. These building blocks are called unit cells. Different materials can have different shaped and sized unit cells. And then the blocks are stacked together to make the larger material, just like building blocks when you were a kid. There are some common unit cells, or what is called crystal structures. One is the face-centered cubic. This is a basic cube or block. There is an atom positioned at each corner and an atom at each face of the cube. Some metals that have this structure are gold, copper, and silver. Another common crystal structure is body-centered cubic. This is also a basic cube. There is an atom positioned at each corner and an atom in the middle of the cube. Some metals that have this structure are iron, chromium, and tungsten. The last crystal structure that we will cover is the hexagonal close packed. This structure has a hexagon on the top and bottom. There are atoms positioned at each vertex and one in the center of the hexagon. And then there are 3 atoms in the middle arranged in a triangle. Some metals that have this structure are titanium and zinc. So, crystal structures seem pretty straightforward. If we have gold, all the positions in the face-centered cubic are filled with gold atoms. And if we have iron, all the positions in the body-centered cubic are filled with the iron atoms. And if we have zinc, all the positions in the hexagonal close packed are filled with zinc atoms. But how often do we have pure materials, pure gold, or pure iron? And what about ceramics, which contain both metal and nonmetal atoms? What happens then? Well, 2 different things can happen. One, the other element can take the place of the host atom, like in the case of the ceramic tungsten carbide. In this case, the carbon takes the place of the 3 tungsten atoms that would normally take up position in the middle. This is called substitution. The carbon substitutes for the tungsten in a normal lattice position. 2. The other element takes up positions in a place that is not a normal lattice position, like in the case of the ceramic silicon carbide. In this case, the silicon takes all the normal face-center cubic positions, and the carbon takes up the spaces along the sides of the cube, the spaces in between. These spaces are called interstitials. So what about amorphous materials? Remember, amorphous materials don't have any repeating pattern like crystalline materials do. The most common amorphous ceramic is glass. However, glass can be made crystalline if it's processed in a specific way. Then it's called a glass ceramic. You probably have encountered this in the top of a stove. One big advantage of glass ceramics over regular glass is its low thermal expansion coefficient. I guess that's why they use it in stovetops. The biggest class of materials that is amorphous is polymers. So how are polymers put together? Polymers are made up of long chain molecules. Let's take a look at polyethylene. Polyethylene is used in a lot of plastic bottles and bags. It all starts with the ethylene monomer. That keeps hooking up with more ethylene monomers in a process called polymerization. And you end up with a very long chain called polyethylene. The same thing happens with chloroethylene. They hook up all those monomers and create polyvinyl chloride, or PVC. And the tetrafluoroethylene monomer creates Teflon. So polymers are really long chains. Now what? Well, a lot of chains get together and form what I like to call a plate of spaghetti. Within the strands, we have covalent bonds, but between the strands, we only have secondary bonds, if we're talking about thermoplastics. We'll talk about thermosetting plastics later. And that's why thermoplastics are generally weak, because the chains are held together by secondary bonds. Well, that's how materials are put together. Some are very organized and some are not. A lot like people, I guess. What category do you fall into?